Hello ladies and gentlemen, and welcome. In the first video of the statics course, we would like to show you how to determine the resultant of two perpendicularly acting forces with a common point of application. Let's take a look at an example. We have a body that is acted on by two forces, a horizontal force, F1, with a magnitude of 15 Newton, and a vertical force, F2, with a magnitude of 10 Newton. These two forces converge at a common point of application, which is right here in the middle. As already said, these forces act perpendicularly to each other, where we have a right angle here. Now, on this body we have a similar situation where the forces are shifted adrift a little bit. However, it doesn't matter for the calculation of the resultant as long as their lines of action still converge at the common point of application. Let me show you. I'm going to draw the lines of action by putting dashed lines for F1 and for F2. And as you can see, the lines of action all intersect at the common point of application in the middle. So that's our example, and our objective is to calculate the magnitude and the direction of the resultant of these two forces. Before we start with the math, let's first add the forces in form of vectors. So, how do you add force vectors? Well, you just start with drawing the vector of the first force, which in our case is F1. So I'm going to draw the first force vector of F1. And the force vectors are added by simply connecting the origin of the consecutive force vector to the tip of the previous force vector. So in this example, I'm gonna start at the tip of F1 and draw F2. And that's gonna give me something like this. So that's my second force. And to obtain the resultant of these two forces, you simply connect the origin of the first force to the tip of the last force. And that's going to give me something like this. Okay, so that's my resultant force vector of these two forces, which I'm going to label as FR. So we have performed a force vector addition on a graphical basis, but now we're interested in finding the magnitude and the direction of the resultant. By the way, the addition of force vectors is commutative, meaning that the order in which you add the force vectors doesn't really matter for the resultant force vector. In other words, whether you add F1 plus F2 or F2 plus F1 will not impact the direction and the magnitude of the resultant force vector. Let me demonstrate it quickly. So I'm going to start with F2 and I'm going to add F1 to it using the same rules as I have outlined before. And the resultant force vector will be no different than the resultant force vector that we got in the previous addition. So this resultant force vector is identical to this one. And this means that the order in which you add forces doesn't matter on the graphical basis. Now, remember, our objective was to calculate the magnitude of the resultant force vector, FR. And if you look closely, you will notice that the three force vectors represent a right-angled triangle, where the right angle is here between the two forces F1 and F2. And since we're looking for the magnitude of FR, we need a mathematical tool that allows us to calculate the lengths in the right-angled triangle. And one of the tools that might come in mind, and which you probably know from your high school math classes, is Pythagoras' theorem. Remember, Pythagoras' theorem states that if you have a right-angled triangle, which I'm gonna draw, so you have one leg, another leg, and the hypotenuse, which is the longest side of a right-angled triangle. Pythagoras' theorem states that if you label the two legs with A and, sorry, it's just A and B, not A and B squared. So, if you label the legs with A, B, and the hypotenuse with C, Pythagoras' theorem states that A squared plus B squared is equal to C squared. And if you want to rearrange that equation into C, you're gonna get C is equal to the square root of A squared plus B squared. That's Pythagoras' theorem. And since our force vectors represent a right-angled triangle, the hypotenuse is basically FR. So we're gonna change the statement into one that includes our forces, and that statement is gonna be FR equals square root of F1 squared plus F2 squared. These are our legs, A and B, which represent the forces F1 and F2. Oops, sorry, I've missed a square here. And all we need to do now is simply to plug the values into F1 and F2. So, let's go ahead and do that. Fr is equal to the square root of, now F1 is 15 Newton. And remember, you need to square both the number and the unit, plus 10 Newton to the square. And that's equal to Fr is equal to the square root of 225 Newton squared. Now remember, since we squared both the number and the unit, we have a Newton square here, plus 100 Newton square. Okay? And that gives us Fr is equal to the square root of 325 Newton squared. And that is equal to 18.03 Newton. So we have taken the square root of 325 and Newton squared, and that gives us 18.03 Newton. And that's the magnitude of our resultant force vector. So we got the magnitude of the resultant force vector, but there is something else that we're looking for, and that's the direction of the resultant. So I'm going to write down So, the direction of Fr is usually expressed as an angle between Fr and the horizon. In our case, that angle is between Fr and F1, and I'm gonna denote that angle as alpha. So, we're looking for alpha. And to compute that angle, we need to use another trigonometric tool, and that's going to be the tangent. The tangent is equal to the opposite leg divided by the adjacent leg. So that's going to be tangent of alpha is equal to the opposite leg, which is at the opposite side of alpha, divided by the adjacent leg. And the adjacent leg is simply adjacent to alpha. Now, in our case, the opposite leg is at the opposite side of alpha, and that's F2. And the adjacent leg is adjacent to alpha, and that's F1. And that is equal to 10 Newton divided by 15 Newton. So, the tangent of alpha is therefore equal to 0.67. That's 10 Newton divided by 15 Newton, rounded up to the nearest 100th. Now, to calculate the angle alpha itself, we need to inverse the tangent, and that gives us alpha is equal to the inverse tangent of 0.67, and that is equal to 33.69 degrees. So that's how you calculate the direction of the resultant. You just use the tangent. Now, sometimes you might be looking for the angle between FR and F2. And how do we find the angle between FR and F2? Well, first of all, let me denote that angle as beta. And if you want to calculate beta, then your opposite leg is going to be F1 right here, and the adjacent leg is going to be F2. So beta is therefore going to be the inverse tangent of F1 over F2. That's equal to tangent minus 1 of 15 Newton divided by 10 Newton, and that is equal to 56.31 degrees. So now we've gotten the magnitude and the direction of the resultant. In fact, we got the direction in both angles, alpha between FR and the horizon, and beta between FR and the vertical axis. Okay, I hope that video was helpful to you in calculating the resultants of force vectors, and in the next video I will show you how to calculate the direction and the magnitude of the resultant of non-perpendicular forces. So stay tuned and see you later.